Okay, this is going to be the lecture over chapter 10, which is going to be looking at rotation. Got several notes there that you can go back through, and I'll make sure that this is available. Actually, it should already be available out there on the Canvas homepage. What we're going to do in this chapter is discuss how to take Newton's laws and apply them to a body that is rotating. How is that motion described? How does that motion change? And we're going to need some new concepts in order to be able to express them, but many of the same concepts are going to carry over from what we had before. Those new concepts are going to be torque, and they're going to be rotational inertia. A rigid body is rotating as a unit, as it's all locked together. The object may be a little odd, oblong and whatnot, very irregular, but as long as it rotates as a unit, that's what counts. We're going to look at rotation around a fixed axis. And we'll go through some examples there to kind of show what that means. Those types of restrictions are going to end up excluding certain cases, such as the sun, where layers of gas are rotating separately. A rolling bowling ball, where we have not only rotation, but we also have translation. So we're not going to look at that as of right now. As you might guess, the fixed axis is going to be called the axis of rotation. This figure and the one that follows is going to show a reference line, and the angular position of this line and of the object is taken relative to a fixed direction, the zero angular position. So in this particular case, let me blow this up here a little bit. So we've got a reference line here, and it's part of the body, and it's perpendicular to the rotation axis. And you're going to use that to measure the rotation of the body relative to a fixed direction. So you've got the axis around which it rotates, you've got the body, and then you've got the reference line. This reference line is going to tell you more about the angles through which it rotates. Okay. The body has rotated counterclockwise by this particular angle. So you've got the reference line here, which is moving through relative to this. And this is going to be considered the positive direction. If it rotates counterclockwise, that's going to be considered positive. If you look at that dot, then that means the rotation axis is out towards you. You're looking at it as the point is coming up. Again, you have R here, which is going to be the radius, and then you've got S here, which is the arc length through which it's rotating. Now we're going to measure this using radians. The radian measure, again, is going to be the length of this particular arc divided by the length of the radius. And that's how our angle is going to be described. It's not going to be described in degrees, but in radians. If you go through an entire revolution, you're looking at 360 degrees. 360 degrees is going to be the same thing as 2 pi r. If you divide that by r, then you have 2 pi radians. And don't reset theta to 0 after a full rotation. Just keep going. So we know all there is to know about the kinematics of rotation if we have theta as a function of time for an object. We're going to define displacement as the angle at which it stops minus the angle at which it starts. That's going to be the change in theta. Clocks are negative. What that means is that an angular displacement in the counterclockwise direction is positive, and one that goes in the clockwise direction, following the arms of a clock as they rotate and track time, is going to be considered negative. So a disk can rotate around its central axis like a merry-go-round. Which of the following pairs of values for its initial and final angular positions, respectively, give a negative angular displacement? So as we go from -3 radians around to 5 radians, as we go from -3 radians to -7 radians, and then 7 radians to -3 radians. So let's kind of draw that out. If we look at the first part here, create a set of axes here. And let's see how much of a circle I can draw here. And I'll also need an eraser. Okay, so I'm going to start here with part A, which I just erased. Let's just try this. We start here at around -3 radians, and we're going to rotate around to about 5 radians, which means we're going to go spinning around, and I'll come in a little bit to kind of show you a little bit around to here. So we started here, ended here. If we're looking at negative angular displacement, we're actually moving in the counterclockwise direction, which is going to be considered positive. So part A here is not going to qualify. If we look at part B, which I'll again start right about here, and we're going to go to -7, that means we're going to head around that way. We're moving in the clockwise direction. That is going to be considered a negative angular displacement because we're moving clockwise. And then finally, part C, where we've got 7 radians, which is going to put us probably right about here. And then we're going to work our way around to -3 radians, which is going to be over this direction. So for part C, we start here, we end here. Our rotation is going to be clockwise, which means we're going to have a negative angular displacement. We start here, we end here, we're moving in the clockwise direction. That is negative angular displacement. So, average angular velocity. Angular displacement during a particular time interval, particularly if we're looking at the average here, it's going to be expressed as the change in the angles divided by the change in time, change in theta divided by the change in t. If we look at it at instantaneous angular velocity, or the limit as the change in t goes to 0, that's going to be your calculus derivation, or d theta dt. If the body is rigid, these equations hold for all points on the body, and the magnitude of angular velocity is going to be the angular speed, just like the magnitude of linear velocity is going to be the linear speed. So figure 10.4 shows the values for the calculation of average angular velocity. So we've got our angle. It's moving this way, so we've got theta 2, which is where it ends up, and then we got theta 1, which ends here. That change in theta. We've got our time here where it ends, and the time there where it starts. So this change in the angle of the reference line is going to be equal to the angular displacement of the body itself during the time interval. So the average angular acceleration is basically going to be the change in your angular velocity with respect to time. Shouldn't surprise you there. And then the instantaneous angular velocity, which actually I believe should be instantaneous angular acceleration. I think there's a mistake in the slide there. The limit as the change in t goes to 0. So alpha ends up being the limit as the change in t goes to 0. So that's d omega dt. So if the body is rigid, then these equations hold for all points on the body. Seems a little counterintuitive, perhaps, but if the entire body is rigid and rotating at the same speed, then all points will be headed, those equations will be true for all of those points. With the right-hand rule to determine direction, angular velocity and acceleration can be written as vectors. If the body rotates around the vector, then the vector points along the axis of rotation. Angular displacements are not vectors because the order of rotation matters for rotations around different axes. This chart may very well come in handy for you. It is a correspondence. And that correspondence is trying to show you the difference between linear and angular movement. And you can see these kinematic equations in the linear form from chapter 2, and you can see how they correspond to the angular form in chapter 10. And you can see their corresponding, their counterparts. So here's another quiz. In 4 situations, a rotating body has an angular position of theta as a function of t, given by theta is equal to 3t minus 4, and then you see it for B, and then C, and then D. To which situations do the angular equations of table 10.1 apply? They apply when you have a constant angular acceleration, just like you had a constant linear acceleration that would apply. Here you have to have a constant angular acceleration. Well, the only way you've got that is if you take the second derivative of these expressions and see if you end up with a constant or if you end up with 0. That will happen with part A, and it will also happen with part D, because by the time you take the second derivative there, you're going to end up with a constant or 0. For B or C, that will not hold true. If you do the chain rule there, you can figure out why. Okay. How are linear and angular variables related? They are related by r, the radius. It's going to be perpendicular distance from the rotational axis. So the position, again, this has to be in radians. Your arc length is going to be the same as the angle multiplied by the radius. The speed is going to be, again, this is going to be in radian measure. The speed, v, is going to be equal to omega times r. And again, if you divide, rework the equation, divide both sides by r, you can, might be a little more easy to see. And then you can express the period in radian measure, where the time it takes you to complete that is 2 pi divided by your angular velocity. Tangential acceleration is going to be your angular acceleration times the radius. And you can write the radial acceleration in terms of angular velocity, where you've got v squared over r. And if you make the substitutions here for v, which come from right here, then you can see where you have omega squared times r. So let's focus on this a bit. Actually, let's go a little bit. Okay, so you've got a circle that is traveled by the point P. You've got the rotation axis, you've got r that extends out this way, and then you've got the velocity off this way. So the velocity vector is always tangent to the circle around the rotation axis. And that should come as no surprise, because that's how we've looked at uniform circular motion up to this point. The acceleration always has a radial, centripetal component. That's something that we had seen before. But it might also have a tangential component as well. So a cockroach rides the rim of a rotating merry-go-round. If the angular speed of this system, in other words, a merry-go-round plus the cockroach, is constant, does the cockroach have radial acceleration and tangential acceleration? So if the angular speed of this system is constant, let's see if I can draw this out. Get our merry-go-round there. Let's see. I'm going to put, can't really put a bug out there, but I can put an X. Your cockroach. So if we have angular speed of the system is constant, then we don't have any angular acceleration. We do have acceleration in towards the circle. We do have linear velocity, which goes out this way. It's tangent to that. So we will have a radial acceleration. We've already seen that up to this point. But will we have a tangential acceleration? In other words, is this advancing more quickly? Is that speeding up? The radial acceleration, yes, because we have the velocity vector that's changing all the way around. But we don't have tangential acceleration. That acceleration remains the same because our angular speed is constant. If omega is decreasing, does the cockroach have radial and tangential acceleration? If our angular speed is decreasing, then we have a deceleration going on. So not only do we have the radial acceleration as we had before, since it's moving in uniform circular motion, but now since this is decreasing, then yes, we have tangential acceleration. All right. So now we're going to apply the kinetic energy formula for a point particle and sum over all the particles. Different linear velocities, same angular velocities for all particles, but possibly different radii, which means you're going to have different linear velocities because those parts of the object that are further out from the radius are going to be moving faster than those on the inside or closer to the axis of rotation. Then we write velocity in terms of the angular velocity. So if we replace v with omega r, then we can see how this changes. We end up with the angular acceleration here being squared, but rather than just have the mass out here like we do with linear velocity, now we've got this funky looking term here that has the radius, not only the radius, but the radius squared involved with it. That's not something that we're used to seeing up to this point. So what we're going to do is we're going to group this off. Every one of these terms has a half with it, so we're just going to take that part out, and then we're going to deal with this part. And that quantity in parentheses is going to be called the rotational inertia, or the moment of inertia. And the reason that's the case, we have learned up to this point that the mass is going to be what resists the change in motion. That's what it's going to be. Now, when we're looking at angles, it's not only going to be the mass that we're going to have to mess with, but we're also going to have to look at the radius. How is that impacting the fact that the object doesn't want to move and has to be forced to move? So that's going to be part of the equation as well. So this is a constant for a rigid object and a given rotational axis. And we always need to specify the axis for I, because that's one of the requirements. Otherwise, we can't establish exactly what the radius is. How do you establish the radius if you don't have the axis established? So we can write the moment of inertia, or the rotational inertia, as I is equal to the sum of m sub I r sub I squared. Now that squared term there is going to come into play pretty heavily later on here. So we're going to rewrite the kinetic energy as the kinetic energy is equal to 1/2 I omega squared. It's in radian measure. So we're going to use these equations for a finite set of rotating particles, and rotational inertia corresponds to how difficult it is to change the state of rotation. Here we have, if the axis is going through the long part of whatever this tube or rod happens to be, then the rod is easy to rotate on that axis of rotation. A little bit harder to rotate it around the middle like this. And you can probably see why. Once the mass, even if this is uniform, the mass really doesn't change. But once you start multiplying it by the radius, and once that radius starts to get pretty far out, then the moment of inertia really starts to resist that change. So the mass has an effect, but that square on the radius is really going to have is really going to start to govern pretty strongly over the mass term. Okay, so here we've got a figure that shows 3 small spheres, and it's given the mass of each. They're rotating about this particular axis, and you can see the radius of each one of those. So rank the 3 spheres according to their rotational inertia about that axis with greatest first. Now, to give you a heads up here, the answer is that they're all equal. And you may be able to see that immediately here, and maybe not. Let's take a look at the first one. I is going to be equal to, you've got 1 meter squared. Let's go with kilograms first. 36 kilograms times r squared, which in this case is 1 meter. That's going to be equal to 36 kilogram times. Right. So what about the second one? 9 kilograms times 2 meters squared, which is also going to end up being 36 kilogram meter squared. Take a look at the third one. 4 kilogram times 3. All of them are the same. Remember, the mass is being multiplied by the distance squared. And the masses, as you keep getting further out, they don't have to be as big in order to have rotational inertia. So let's say that you have a continuous body and you are attempting to determine the rotational inertia. If you're going to use calculus, basically, you're going to take the radius squared and multiply it by dm and integrate that over the entire mass that you have. In principle, you can use that, but it can get complicated. So we have a set of common shapes for which values have already been calculated because we're nice like that. If you want to work through the math of some of these things, it's worthwhile to do if you've got buckets of spare time to do so. But you can kind of see, you've got your axis, you've got how this is oriented. You can see the differences here and how that moment of inertia comes about. So if we know the moment of inertia for the center of mass axis, then we can find the moment of inertia for a parallel axis with the parallel axis theorem. So the axes have to be parallel, and the first has to go through the center of mass. There's no getting around that. You got to do that. It does not relate the moment of inertia for two arbitrary axes. In other words, it can't be perpendicular, they can't be askew. You just can't throw it out there and just say, well, this works. There are certain criteria that have to be met. So we need to relate the rotational inertia around the axis of P to that around the axis of the center of mass. So we have our relationships here. The figure shows a book-like object where one side is longer than the other, and there are 4 choices of rotational axes, all perpendicular to the face of the object. Rank the choices according to the rotational inertia of the object about the axis with the greatest first. Okay, if you were to do that, you're going to have to remember here that the further these mass points are away from your rotational axis, the harder it is to get this object in motion, because the moment of inertia not only depends on the mass, but it is more dependent on how far away they are from the axis. In this particular case, case number one, look at how far all of these masses, if you look at it as individual mass particles, look at how far away they are from the axis here. Radius is going to be quite big, and since that term is the one that's squared, this rotational axis is going to have the most. That's why it comes first. The second axis here is going to be closer, but it's still going to have points that are way further out than what you would have at either 3 or 4. Not as much as what you have with 1, but definitely more than 3 or 4. That's why it falls second. If you look at 3 and 4, what you are noticing with 4 is that these objects out in the corners here are going to be further away from the axis than what they were as if the axis were drawn here. Here they're going to be fairly close. That's why 4 gets ranked a little bit higher than 3. It's because of the radius of the object away. So, calculate the moment of inertia for figure 1013. In other words, we have rotation axis through the center of mass right here. It doesn't necessarily have to go through this way. It just has to go through the center of mass. So we have the rotation through the center of mass here. And since we're looking at part B, what has happened here is that that rod has moved, that rotation has moved here to the end of the rod rather than remaining here. Since this is the case, if we were to go through and to sum that by particle, if you look at it here and you want to sum that together just by each particle, this is not away from the rotation of axis, so that's why we've got a 0 here. This point right here is actually a length L away, so we put that in here, and then boom, we got it. That's the moment of inertia. If we were to use the parallel axis theorem, then we would have the moment of inertia as it rotates through here plus mh squared. So if we go through and we determine, we know what the moment of inertia is here. I'll leave you to figure that out. Plus what we have here for these 2 points and how far away they are from this axis. And then you can put all of that together, and then you come up with the same thing. So by using the parallel axis theorem, we come up with the same thing as if we sum it through by particles. Sometimes it's a little bit easier to use that, other times maybe not, but it's always something to keep in your back pocket. All right, torque. This is the force necessary to rotate an object, and that depends on the angle of the force and where it is applied. And we can resolve the force into components to see how it affects rotation. So we've got torque due to this force, which causes rotation around the axis. You have force being applied here to making a certain angle. So we can calculate the same torque by using this moment's arm distance and the full force of the magnitude. What we are going to find out is that it's only the tangential part of this particular force which is going to cause rotation. It's not this part right here, but it's going to be this part. We'll see that in the formula coming up. So torque takes these factors into account. So the torque is going to be equal to the R, the rotational radius, times F, and then times the sine of the angle that is in between those two. You can see that here. You've got this, and then you've got this. They make an angle with each other. So the sine of that is going to be taken into consideration as far as the application of torque. And if you remember your trig, you will remember that the sine of 0 is 0. So if they're all in the same line, you're not going to get any torque. It's only when you get to the point where you're pushing perpendicular to the radius there that you're going to start seeing a maximum amount of torque be applied. So a line extended through the applied force is called the line of action of the force. The perpendicular distance from the line of action to the axis is called the moment arm. Units of torque are going to be the Newton meter. Now, it just so happens that a Newton meter and the joule are equivalent, but you never express torque in joules. It's not really considered to be energy. That's why they use the Newton meter. Torque is going to be considered positive if it causes a counterclockwise rotation. Otherwise, it's considered negative. If you have several torques going on at the same time, the net torque or the resultant torque is the sum of the individual torques, just like the linear forces are. So this figure shows an overhead view of a meter stick that can pivot around the dot at the position marked 20. All 5 forces on the stick are horizontal and have the same magnitude. So rank the forces according to the magnitude of the torque that they produce, with the greatest first. Well, you have a force being applied this way and a force being applied this way that are equal distant away. Both of these are at right angles to this particular arm. Because of that, you're going to get the maximum amount of torque out of these guys. That's why they're listed first. Then if you go and if you look at the others, and what about 2, 4, or 5, both 4 and 2 are what's probably close to the same angle away from the arm. But this guy over here is going to be a little further out along the arm than this one. Because of that, you're going to be looking at putting F4 first, and then F2 is going to be next to last because it's close to the pivot point. Finally, F5 is actually pointed in the same direction as the meter stick. And because of that, the sine of the angle between those two is going to be sine of 0, which is 0. So it's doing nothing as far as torque goes. So, because you didn't have enough to worry about, in rotational motion, we're going to take force is equal to mass times acceleration, and we're going to rewrite it with rotational variables. So the net torque is going to be equal to the moment of inertia times the angular acceleration. And the torque that causes angular acceleration, let's see if I can put that in here a little bit. The torque due to the tangential component of the force causes an angular acceleration. This is the tangential part here. So, Newton's second law for rotation, you've got a figure that shows basically the same kind of thing as what you had before. You've got a force that's over here to the left of what's considered to be the pivot point. You've got two horizontal forces. You've got F1 and F2 that are applied to the stick, but only this one is shown. So force F2 is going to be perpendicular as well to the stick and applied to the right end. In other words, we know it's going to be over here. So if the stick is supposed to not turn, in other words, remain stationary, what's going to be the direction of that second force? And should it be greater than, equal to, or less than the first force? That force should point down. It should point down because what you've got, something is forcing on this particular arm to go this way. You're going to need something to counterbalance what's going on over this way. Now, it also says here that it should have a smaller magnitude. And why is that the case? Well, as we've seen previously, scroll back to it, torque is going to be equal to the radius times F sine of theta. The sine of theta is going to be the same. It's going to be perpendicular here. So torque becomes a factor of not only R, but also of F. Since this length of R over here for this particular force is going to be much less than the R that's stretched over here, that means in order to produce the same torque, you're going to need less force out here in order to be able to accomplish that. So you'll also see some comparisons here between energy and work. The rotational work kinetic energy theorem is going to state that the change in the kinetic energy is going to be the same as the change in the moment of inertia times the square of the angular acceleration. And that's going to be defined as work. So the work done in rotation about a fixed axis is going to be basically taking the torque multiplied by d theta, integrating it to the final and then the initial positions. If you have a constant torque, then that integral reduces down obviously to just this. How is power related? Well, if we remember back, power is going to be basically how much work can be applied over a set amount of time. And in this particular case, it's going to be the torque times the angular velocity. So again, we have a table here which is going to show the differences in the position in a purely translational and then a pure rotational. X corresponds to theta. The velocity is going to correspond to omega, which is your angular velocity. Acceleration corresponds to angular acceleration. Mass and rotational inertia, those are going to be equivalent concepts. Newton's second law, and then the definition of work. Going on, you're going to see the kinetic energy. So you can see the comparison of mass and moment of inertia and velocity and angular velocity. Power, force times velocity, torque times angular velocity. And then the work kinetic energy theorem, which is the change in kinetic energy is going to be the same as the work in both cases. So the summary here will encapsulate all of the things that we've covered in this particular lecture. If you have any questions about it, please do let me know.